Yo, 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 sup, peeps. Alright, so today we're going to keep going with rate laws. Okay, and then we're going to get into some of the effects on temperature. So that's the plan for today. Alright, so there are actually more than one type of rate law. Alright, so remember that's that mathematical relationship. So we've been studying or been dealing with what's called the differential rate law. Okay, so this is what we've been working with. And this differential rate law shows us how rate depends on concentration. There's actually a second type of rate law. And it's called the integrated rate law. So the integrated rate laws actually show us how concentration depends on time. And the integrated rate laws actually give us the half-life of the reaction. The reaction, or the reactants, I guess we can say, now this can be found, these integrated rate laws are actually found right from our differential rate laws. Right? So, and it's a mathematical relationship, and we can integrate these rate laws. We could do those math derivations, but we're not going to. Right? So this can be found by integrating the rate law of 0 first and second order reactions. Now, these are actually, integrated rate laws are really, they really make our lives simple. Okay, the equations are kind of a pain in the butt, but it allows us to do some things and do some calculations that make it a lot easier. So these equations, our integrated rate laws, allow us to calculate the concentrations at any time after the reaction has started. So once the reaction started, we can use the integrated rate law to figure out how much, what the concentration of our reactants are. Right, which is really, really nice. Okay, so let's kind of do a summary of the orders and their different types of rate laws. And let's start with zero order. So remember, our zero order does not depend on concentration. And our differential rate law would be our rate equals our constant times the concentration of A to the zero order, or our rate equals K. So remember, anything to the zero is a 1, that's why it ends up just being K. Now, in reality, these reactions are usually catalytic reactions. These are reactions that are catalyzed, okay, with a catalyst. So, for example, decomposition of hydrogen peroxide, 2H2O2 goes to 2H2O plus O2. So this will happen naturally over time, but it's really, really, really slow. All right, and this is a zero order reaction, so what that really tells us is that the concentration, or whatever the concentration of this H2O2, it doesn't matter. When we catalyze this, it will go really, really fast. All right, but again, it doesn't matter what this concentration is. All right, it's not going to affect my rate. Now, we can take this rate law up here, okay, this differential rate law, and we can integrate it. We're not going to do that math. I'm just going to give you what it turns out to be. So our integrated rate law would be this. The concentration of A at time t minus the concentration of A originally equals negative K times T. So now let's just kind of run through what this means. So this is a T. This is the concentration at a very specific time during the reaction. This is our initial concentration. Okay. We know what K is our constant, and T is time. So if we know our constant, if we know time, and we know our initial concentration, and this is a zero order reaction, we can figure out the concentration at any time during a reaction using this equation. Now, if we plot concentration versus time in a zero order reaction, we get this. And you need to know these graphs. All right, so this is concentration of A versus time. And in a zero order reaction, okay, this is going to do something like this. So our slope in this integrated rate law for a zero order reaction is actually equal to negative rate. Or really what happens is our slope is equal to our negative of our constant. All right, so when we plot a zero order reaction, okay, you will get this straight line. So if we plot the concentration of A versus time, and it's a straight line, that will tell you that it's zero order. Okay, so you have to know, okay, they may ask you about this graph. Okay, so they may say, hey, all right, here's this graph, what order is it? Right? And you should be able to look at it and say, okay, look at our concentration change over time is just a negative slope. It's straight. That's going to be zero order. So you have to be able to use that. Okay. All right. So this is our summary of our zero order. So you have our differential rate laws, okay, which is up here, and then this is our integrated rate law that we're going to be able to use. So let's talk about first order. So in our first order reaction, our rate law the sum of the exponents is 1. So usually our differentiated rate law is going to equal rate times our constant times the concentration of A to the first. Okay. Now, we can have numbers other than 1. All right, so you can have fractions. All right, and generally it's going to be a half or a third. All right, so you can have those. All right, so for example, we could have this rate law would just be something like A going to B. But we could have something like A plus B going to AB. And for this to be a first order reaction, we could have rate equals K times the concentration of A to the 0.5 times the concentration of B to the 0.5. Right? This would add up to a first order reaction. Right? Or, okay, so this is one possibility. Another possibility would be our rate is equal to K times A to the first, B to the 0. All right, but again, that's really that guy up there. Okay, because this is really 1. All right, this concentration doesn't change. Okay, so this is some ways that we can get first order reactions. Okay. Now, so this is our differential rate laws. Right? We can integrate that rate law. And this is for second order, or excuse me, for first order. And this is natural log of the concentration of A at time t minus natural log of the original concentration equals negative kT. Right, and again, this is the concentration at a specific time. This is our initial or original concentration. This is our constant. And then this is time. So again, this is giving us, we're going to be able to calculate concentrations at specific times during a reaction with this equation. Right? That's what this is for. And this equation is only for first orders. Right? So let's try a problem with this one just for fun. Right? And do I have enough room on this page? I probably have enough room. It's going to be tight, so let's just flip it over. So let's just do this. A certain first order reaction has a rate constant of 4.5 times 10 to the minus third per second. How much of a 50.0 milliliter sample will have reacted after 75.0 seconds? Right. So now it tells us that it's first order. Okay. We're trying to figure out a specific concentration at a specific time, so we're going to use the integrated rate law for first order. Okay, so we're going to use ln A at time t minus ln of A original equals negative kt. So now we can substitute. This is what we're trying to calculate. Okay, we know this. Okay, it gives us our original, which is 50 milliliters, and we want that in liters, by the way. So we're going to have to convert to liters. All right, so this is 0.050 liters. So we got ln of 0.050 liters equals negative 4.5 times 10 to the minus third per second times 75.0 seconds. All right, so when we do this math, we get ln concentration of A at time t, and that turns into plus 2.995 equals negative 0.3375. So then we got ln concentration of A at time t equals negative 3.333 so we get the concentration, we do this math, at time t is equal to 0.0356 molar. Okay. So this would be the concentration of the sample after 75.0 seconds. Hold on, did I mess this up? Oh, I see. This is not. I messed up units. Can't read my writing. So this isn't supposed to be millimeters. This is supposed to be millimolar, which turns into a 0.050 molar solution. So that's a 0.0356 molar solution. Right, so this is our concentration after 75 seconds. All right, now the question actually asks for how much of the sample is left, okay, that hasn't reacted. So we know that we have 50.0 millimolar to start. We know that 0.0356 molar, or 35.6 millimolar, is what's left. All right, so we want to know how much is reacted, so we actually have to subtract. So that's 14.4 millimolar. So this is what is actually reacted. Yeah, that was a fail. I'm sorry, I messed up units. All right, so let's just kind of run through it one more time. So we have this first order reaction. All right, here's my rate constant. This is my concentration. All right, and it's gone for 75 seconds. So here's my integrated rate law for first order. All right, so we stick in my concentration of 0.050 molar, because I converted from millimolar to molar. All right, I have this rate constant and my time, and then I do my math. All right, and then this is my molarity of the concentration after 75 seconds. Okay. Originally, the question says how much of the sample will have reacted. So we start with our original concentration, subtract off our final concentration, and this is the concentration that actually reacted. Okay, so that's the question. Sorry about that. That was my bad. Woo. Okay. Now, just like zero order reactions, this has a graph that you have to know. So we're still in first order. If we plot concentration versus time in a first order reaction, like we did for zero order, this time we get this. Right, so this is not integrated, but if we plot natural log of the concentration of A versus time, this is where we get that straight line. And again, our slope, our slope of this line when we plot it is negative. Okay. So if you see the natural log of the concentration of A in time with this straight line, okay, this graph tells us that it's first order. So a first order reaction has a constant half-life. Okay, so first order reactions have a constant half-life. So this is where our T1/2 equals 0.693 over K. Right? And this is actually the half-life of the reaction. And this is where our radioactive isotopes sit. All right, so this is for first order reactions. Let's deal with second order reactions. So so let's talk about our differential rate laws. Okay, and we could get them a couple different ways. Normally, you might see it this way: rate equals the concentration of A squared. Okay, so that would be second order. Or we could have rate, oh, I forgot the K. Rate equals K times A1 times B1. That would be second order. So these are, okay, our differential rate laws that you could see. All right, now, our integrated rate law. So if we integrate this, okay, now if we integrate this, we get 1 over the concentration of A at time t minus 1 over the concentration of A original or initial, and this is equal to KT, no negative. Okay. And again, this is going to give us the concentration at any time during the reaction. Now, the graph. If we see concentration of 1 over the concentration of A versus time, okay, it's going to look like this. And our slope is equal to K. This is the graph of our second order process. And again, you would have to be able to pick this out. Okay, you would have to be able to say, hey, okay, if we were to graph this integrated rate law, this is what it would be, and it would be second order. Or they could show you this and say, hey, what order reaction is this? And you would have to say, hey, it's second order. All right. Okay, so make sure you remember these graphs. Now we're gonna, in practice, okay, you're gonna be using, okay, these integrated rate laws. Okay, so in our homework, you're going to be using them. So you make sure you have these formulas handy. Right? So if you have that second order reaction and we're dealing with changing concentrations at a specific time, we'll use these integrated rate laws. Okay? And we'll practice with them. Okay. So lastly for today, I want to deal with the effect of temperature on reaction rate. And we know the general effect on temperature, or on the reaction rate by temperature. So we know that generally as the temperature increases, the reaction rate is going to increase. Okay, the particles move faster. They have more energy. All right, so because of this, there are more collisions. And they have more energy. Okay, so we have more effective collisions. Okay, so in general, we know this is true. Now, there's actually an equation that there's an equation, and it's called the Arrhenius equation. Arrhenius. So what the Arrhenius equation does, it's an equation for the relationship between the constant K, our rate constant, and temperature. And our equation is this. K equals A E to the EA divided by RT. Okay, so this is the Arrhenius equation. So what does all this mean? Well, K is our rate constant. This AE thing is called the proportion constant. EA, you should already know, this is our activation energy. R is our universal gas constant. And T is temperature. Now, I'm going to be honest with you right up front. I'm never going to have you use this equation. Okay? I'm never going to have you solve this. All right, you just have to understand what the equation is telling us. Okay, so I'm not going to ask you to use it. I will ask you to explain what's happening. All right, so let's write it right here. You will not use this equation, but you must understand the equation.